Okay, so chapter 13 you can divide into 3 main subtopic. If you go through the learning outcomes, you have ideal gas equation, that one is the first subtopic, and then it's about kinetic theory of gases, the second subtopic, and then we have a molecular kinetic energy and internal energy, which is actually under the same subtopic. Okay, but similar things. Okay, and then for ideal gas equation, you guys will learn about this particular equation. I think you guys familiar with this one in chemistry. Then we learn about the 3 main relation: what happens when pressure is constant, what happens when the temperature is constant or volume is constant. And then we will learn about kinetic theory. Okay, we learn what is the assumption that has been made about the molecular motion. And then we have Vrms. And then we also learn about these 2 equations, which is very similar to the which is very similar to the ideal gas equation, but include with the Vrms. Okay, and then obviously once we have the velocity, you expect to have the kinetic as well, which we calculate in the last topic. Okay, so this chapter we focus on molecules that are very small things, and I think you guys are very familiar with this one, where you guys learn in chemistry, so it should be okay. Okay, the list of the formula, if you look through the list of formula, it will be from 69 to 75. So this is the given formula, so you don't have to memorize anything. Commonly student will get confused with the last 2 equation. This one tak ada masalah lah, and this one pun tak ada masalah. I think this one is okay, but the last 2 or 3 then student got a little bit mixed up, but don't worry, we clear things up soon. Okay, so first we start to learn about the Boyle's law, Charles' law, and Gay-Lussac law. So obviously before that, I would like to introduce you the ideal gas equation, where PV is equals to nRT. What does it mean by ideal gas equation? Siapa boleh beritahu? Guys, what is ideal gas? Shazwina, what can you tell about the ideal gas? Shazwina ada? Tak dengar Shazwina. Saya punya sound ni kecil sangat. Siti Aminah ada?
Ada, sir.
Apa tu ideal gas?
Combination of all 3 gas law.
Okay, correct. Very good. So, the ideal gas is actually obeys Boyle's law, Charles' law, and obviously the Gay-Lussac law. So, obeys those things lah. So, we'll start with this equation and we're going to discuss. Okay, so obviously we have, I'm going to erase this one first. We have the 3 main law. We have Boyle's law. You have Charles' law. Okay, and then you have Gay-Lussac law. Okay, the Gay-Lussac also known as a pressure law. Okay, so the first thing that you guys need to do is that you have to memorize for Boyle's law, what is the quantity that is constant. For Charles, what is the thing that is constant, and for pressure law, what is constant. Okay, so Boyle's law, apa yang constant?
Temperature.
Yes, good. Okay, temperature is constant. T constant. For Charles law, apa yang constant?
Pressure.
Yes, P is constant. And then for pressure law,
Volume.
volume is constant. Very good. Okay, I think you guys has memorized this one code already. And then if you don't, if you haven't, then you have to memorize because sometimes they might give you the term like Boyle's chance and pressure law, and you have to deduct the information from that. Okay, so obviously I think you already use this triangle. Pakai kan triangle ni? Oops. Jumpa tak? Pernah pakai this triangle?
Pernah.
Okay. So if T is constant, then basically you put your hand on the T, so you have PV equals to PV. It's as simple as that, right? So it becomes PV equals to PV. Okay. If P is constant, then you will have V over T equals to V over T. Okay, obviously the left hand side is 1, right hand side is 2. And then if V is constant, then you will have P over T equals to P over T. Okay, but you have to be careful with the pressure law. Sometimes when students heard it is a pressure law, then the thing that they, I mean, the first thing that they think is constant is actually pressure, but no, this one is a void. The volume is constant for Gay-Lussac and pressure is constant for Charles law. So if you can memorize those things, and this one shouldn't be a problem, as long as you are using this one. Okay, so far can you guys follow? Any question?
No, sir.
Okay, good. Okay, now we want to discuss about the graph. Okay, obviously this one have a different graph. So I'm going to show you types of graph that they have. Maybe I can copy this one straight away. Copy. Paste. Paste. Maybe one more over here. Okay, for Boyle's law, the T is actually constant. So if T is constant, N and R is constant as well. So the whole thing over here is a constant. So if I want to plot P and then I bring the V to the other side, let's say I plot P against 1 over V, then I will expect to have a straight line, right? Where the gradient will be the nRT. So I'll draw that one first. If I want to plot P against 1 over V, then I expect to have a straight line, okay? Because the T is constant. And then if I want to plot P against V, then this one is against 1 over V, right? Or you have the same graph with 1 over X mean graph, okay? So you have this type of graph, quadratic, tapi doesn't touch the axis. So this one if you plot P against V. So you can see here that you don't have to actually memorize anything. As long as you understand the concept, it should be okay. Okay, the second part, for Charles law, you have P is constant. So this one is constant. I can bring the constant over here. So you have N R over P. And the whole thing over here is a constant. So I will have a straight line if I plot V against T. Oh, faham ke tak?
Paham, sir.
Alright. If I plot V against T, then I will have a straight line. Yeah. And then the last one will be Gay-Lussac, where V is constant. So in this case, I can bring the V down here. So you can plot P against T, and then you will have a straight line. Okay. So to solve this one, most likely you just have to use this three relation. Most likely, no? sometimes you might have to use the ID guess equation. Biasanya soalan dia tak susah, just that sometimes they try to give you more than one punya cases. Contohnya dia gabungkan malls dengan chance, and then student got a little bit confused. But if you do it step by step, then should be okay. Okay, so like I told you before, we have the ID guess equation, PV equals to nRT. And at the same time, you also have a very similar equation, just that you have a different symbol. This one is NKT. Both of them represent the same thing. The only difference here is that the first one in terms of mole and kecil kan, and then the second one too in terms of numbers of molecules and besar. So that's the difference lah, and small and big. And then R and K obviously changes as well. So the P here represent apa? Siapa boleh beritahu? What does the P here represent? Arif? Arif.
Ada sir.
P tu represent apa?
Apa sir?
P tu represent apa?
Pressure.
Yes. Unit dia apa? SI unit pressure apa?
Pascal.
Yes, very good. Okay. V. V tu apa? Azmin ada Azmin?
Ada sir.
Okay. V tu apa?
Volume.
Okay, unit dia apa? SI unit. Azmin? SI unit apa?
M cube.
Yes, very good. M cube. Okay, thank you. Akila. N ni apa? Akila? Tidak. Akila tak nyawa. Farahia.
Yes, sir.
N tu represent apa? Number of apa?
Number of mole.
Yes, number of mole. Unit dia mestilah mole kan? So katakanlah kamu dapat bukan dalam mole, katakan dia kasih dalam mass. Macam mana nak tukar mole? Ya tak? Chemistry. So katakanlah kamu
Bahagi
diberi
molar mass.
yes, kalau N, kalau diberi mass, kamu bahagi dengan molar mass, you will get numbers of mole. Okay, thank you Faria. Katakanlah diberi numbers of atom. Kamu nak bagi dengan apa? Naila. Naila. So Naila tak ada juga. Izzati. Izzati ada ya?
Yeah.
Kalau kamu nak cari mole, diberi numbers of atom, kamu kena bagikan dengan apa?
Avogadro.
Yes, Avogadro. So I think you guys know what Avogadro nilai dia berapa? 6.02 times 10 to the power of 23. Okay, very good. Thank you. And then we have R, which is a constant. The value for R is actually 8.31. Okay. And then we have temperature, which is unit apa? Temperature ni sebenarnya. What is the SI unit for temperature? Yes, Kelvin. So if I have in Celsius, what do I need to do to convert to Kelvin? Macam mana saya nak convert? Celsius to Kelvin. Apa Izzati? Sorry.
Tambah dengan 273.15.
Okay, very good. Okay, so you have to add with 273.15. So Akila kata internet dia tadi start. Okay, it's okay. So So if you want to convert, you really have to convert for this one because you have a constant. So kalau kamu ada equation yang guna constant like R ni, so you really have to use SI unit. So these are the units that you need to use. Okay, jangan pakai unit lain. Then the same thing goes over here. You have PV and then T ni benda sama lah. And then N here is number of molecules ataupun numbers of atoms. Number of molecule. K here is actually the Boltzmann constant. Okay, we call this one as Boltzmann constant. Okay, the value here would be 1.38. Mana tu dia, Alright, over here 1.38 times 10 to the power of negative 23. So I always got confused between the Avogadro number. The Avogadro is positive 23, this one is negative 23. So you guys can confuse lah. Then the K here, actually you can calculate the K by calculating R divided by NA. So 8.31 you divide by 6.02 times 10 to the power of 23, you get that numbers. So basically this is a derived equation if you want to represent the equation in terms of number of molecules. Okay, atas ni in terms of number of mole. So it depends on the question, and then you just have to use the yang mana yang related lah, which one kamu nak pakai. Yang atas ni, okay, normally when we discuss about this one, the N, R dengan dia punya N dengan R tu adalah constant lah, sama juga kat sini. N dengan K tu is constant, maksudnya dia dalam satu enclosed system. Biasanya macam tu. So bilangan atom dia tak bertambah, bilangan mole dia tak bertambah, and the constant memang tak berubah lah. That's what kita ada all these things. Okay. So for any question? No, okay, good. So try to tengok nota kamu in case I miss out on anything. So actually we covered 13.1 and 13.1 lah. We already covered 13.1 and part of 13.2. Okay, so before we go further, okay, you guys need to know about the kinetic theory of gases, the assumption of the kinetic theory of gases. What is the assumption that is being made? So saya malas nak tulis balik. I'm going to copy it from here. Yang pening tutup mata. Mana dia? Okay, so it's this one. I'm not sure if I can copy to the other document. Hopefully I can. Yes. Okay, so for the next subtopic, which is 13.2, okay, we discuss about kinetic theory of gases in detail. So if you go through your lecture note, it says that the macroscopic behavior of an ideal gas can be described by using the equation of state, but the macroscopic behavior only can be described by kinetic theory of gases. So over here they make lots of assumption. Okay, so your notes might tulis slightly different, I might write slightly different, but basically referring to the same thing lah. So number one, it makes up of atoms or molecule. Okay, so dalam satu gas tu hanya ada atoms dengan molecule, tak ada benda lain. Okay, and then it move randomly and haphazardly, means you really it move randomly lah. Nak explain apa tak tahu. And then the volume of atoms and molecules are negligible compared to the volume of the space. Okay, katakan kamu ada enclosed space like this, so the atoms and molecules take up space is negligible compared to the space to punya volume. And it undergoes perfectly elastic collision. So if you guys still remember in chapter 3, you learn about elastic and inelastic collision, and what can you say about the kinetic energy there. Okay, and then intermolecular forces is negligible. So kalau kamu tengok kat chapter 7 gravitation, any object that has two mass will have an attractive force, akan ada potential. But here we ignore the intermolecular forces because the mass is very small. Okay, and then the time during collision negligible compared to the time between collision. Maksudnya waktu ketika pelanggaran tu sangat singkat, dia sentuh sekejap je, so we ignore those things and we just consider the time between collision tu kita consider lah, tapi yang lagi satu tu kita tak consider. So kalau kita consider dia ada main banyak peranan lagi, we have to consider. Kalau kamu tengok chapter 3 kita belajar impulse, so the time for during collision tu main peranan, but here we ignore lah. And then it moves with a constant velocity between collision. Okay, logically kalau dia berlanggar mungkin dia punya velocity slightly changes, but here you assume you move at constant velocity and all the atoms are equal. Kita kira average lah, average punya velocity. Okay, speaking of average velocity, so if you want to describe a velocity of an atom inside a apa orang cakap, container, let's say container, so you have to say about certain values. Akan punya cakap lah value dia apa. So to assume those things, we use the Vrms, okay, root mean square speed. Daripada mana dia datang? Dia sebenarnya datang daripada mean square speed. Mean square speed. Okay, mean square speed ni, dia basically take each individual molecules punya speed and then they take the square. So you have, let's say, v1 square plus v2 square plus whatever that is, and vn square. Contohnya kamu ada container. Okay, kalau kamu ada 3 molecules, then you expect to have v1, v2 and v3 only lah. Kan? And then you take the square of those things, you add all of those, and then you divide by n. Okay. The reason why they square actually because they want to ignore the p negative sign. Okay, kalau dia velocity, you know, it has a direction kan, so dia boleh, I mean, this one is speed, tapi itulah dia ambil square tu sebab tu cari dia kira. And then you have this symbol, we use this symbol lah. So this is what we call v square mean. Mean tu sebab dia bagi dengan total number lah, average. Okay, if we want to discuss about the Vrms, Vrms is actually root mean square of the speed. So basically this one is Vrms. So ini adalah mean square. So this is the mean square. If you take the root of mean square, so you have this thing. Okay, so I can rewrite these terms by substituting this one inside here, okay, and then you get another equation lah. Okay, ini dia punya cara dia derive. Okay, but at the end of the day, the equation that you guys will be using is this one. This one already derived. Okay, so you have two forms. It's either 3kt over m or square root of 3RT over capital M. I have to double check that one in case I mix it up. Betul tak? Can somebody check? Is it correct? Yes,
Betul, sir.
Okay. So the derivation you can refer to the lecture notes. Obviously they actually derive from the PV to punya equation juga, and then they came out with this one. You can go through if you want to. Dia ada dalam page 28 kot. Page 28. Most of the time kalau ditanya Vrms, you can straight away use this formula. So one of the key findings from this formula is that Vrms is actually directly proportional to the square root of temperature. Okay, so if temperature is increased, then you expect the Vrms to increase as well. That's it for the Vrms. And then obviously in this subtopic you also have the yang dia derive tadi equation tadi tu, which is mana saya maybe I can write over here, PV equals to 1/3 and m v square, okay, or p equals to 1/3 rho v square, okay. And because of this, actually you can write one more equation. Yang equation lagi satu ni tak diberi dalam exam. Kadang-kadang boleh pakai, kadang-kadang memang boleh pakai lah, cuma kadang-kadang kamu perlu, kadang-kadang tak perlu pakai, which is this one. So maybe have to move this one a little bit further up. Okay, so the three main equation for Vrms is these three. Okay, yang ni basically di rearrange jadi yang ni je, so tak perlu kamu nak pakai sangat, biasa tak pakai pun. Melainkan kalau dikasih in terms of volume, then you might want to use the first one ni. Okay, saya tengok symbol yang kamu pakai, is it the same? You guys use the same symbol? Yes. Okay, so maybe I just want to rewrite this one better. Cemburuk pula tulisan. Okay. So you might want to use this equation, yang the three important things ni, to find the Vrms, and sometimes you might want to use this one to find a different value such as volume, if you want to calculate the n given the Vrms or things like that. So these two is related, and you can use both of these to solve the problem. Okay, any question?
No, sir.
Okay, there's no question, then maybe you can move to the last subtopic, which is about the molecular kinetic energy and internal energy. Molecular kinetic G and internal energy. Okay. So in this chapter, you have to discuss the translational kinetic energy, degrees of freedom, state the principle of equipartition energy, discuss internal energy of a gas, and solve problem related to internal energy. Okay, I'm going to start with the so I'm going to start with the translational kinetic energy of molecules. Okay. So the first thing that you guys need to know is about translational kinetic energy. Okay. So if you really want to understand this last topic, if you can understand, then if you want to solve, that should be okay. Saya patah balik kat atas ni. Okay, kalau kamu tengok dekat sini, dia ada few equation. So ni yang 13.3 lah. So ada few equation yang student selalu mix up, sebab kat belakang ni semua sama je, dia ada KT. The only difference is yang depan ni. So if you really understand, then it shouldn't be a problem. Okay. First of all, you guys need to understand what is translational. Translational ni adalah dia macam linear punya speed. Okay, so if I want to assume that if I have the molecules, katakan molekul saya adalah H2O, H and O. Okay, this is my molecules. So these molecules logically, linearly, can travel into three directions: y-axis, x-axis, and z-axis. Betul tak? You guys agree with this?
Yes, sir.
And for each one of these, setiap satu direction tu represent square KT. Okay, sorry, bukan square, half KT. So setiap satu pergerakan tu dia represent 1/2 KT. Saya tengok nota kamu dia tunjuk macam mana. So if you have 3 direction, so dia jadi berapa total?
3/2.
3/2 lah. 3/2 KT. So this is the formula that you have lah. Translational kinetic energy for a molecule. Okay, untuk satu molekul. And then if you want to find, okay, if you want to find for total, yang total ni sebenarnya biasanya dia tak ada dalam syllabus kamu, tapi dalam nota kamu ada, so saya tunjuk lah. So KTR ni 3/2 KT ni untuk satu molekul. Okay, so let's say if I have a container, I have 3 molecules. Ada 1, ada 2, ada 3. So saya kena buat apa pula? Macam mana? Kamu rasa?
Sir,
Yes? Betul
boleh
saya?
ulang Sir cakap apa tadi?
Okay. Kalau kamu ada okay, satu molekul ni kan, dia boleh bergerak 3 direction. So setiap direction ni kamu ada setengah KT, setengah KT, setengah KT. So maksudnya satu molekul ni translational kinetic energy dia adalah 3/2 KT. Tambahlah 1/2 tambah 1/2 tambah 1/2. So this is for one molecule. Kalau saya ada 3 molekul ataupun 4 molekul, saya kena buat apa? Saya nak cari semua. Darab, yes, exactly. So if I want to find the total average mean, so it will be E multiplied by, sorry, it will be N multiplied with numbers kinetic energy for each molecule. So numbers of molecule darab dengan KTR, itu kamu dapat dia punya semua. So dalam soalan kamu kena baca soalan betul-betul. Kalau kamu simply hafal formula, then maybe kamu tertukar. Tapi kalau kamu understand konsep dia ni, then sepatutnya tak ada masalah. Okay, and normally they will ask you about KTR. Dia jarang tanya yang bawah ni. So jarang-jarang lah. Most of the time dia tanya untuk satu molekul. Kalau dia kata untuk semua molekul dalam kontainer tu, kamu kena cari N tu dulu. N tu kamu boleh cari pakai volume tu semua lah. Okay, that one is for the translational kinetic energy. Okay, and at the same time, maybe I can explain to you about the equipartition of energy. Tu letter code. Okay, katakan untuk kinetic energy je. Katakan kamu ada bola. Okay, kamu ada bola sepak. Kan? Kalau kamu perasan, if you have a soccer ball ataupun football, kalau dia bergerak, kalau ditendangkan, so one thing yang dia bergerak is that it has a linear motion. Dia gerak. Dia boleh ke depan, ke kiri, kanan atau bawah. Itu dipanggil translational. At the same time, dia boleh rotate. Kamu perasan tak bola ni rotate? So the rotation tu kita panggil sebagai K, rotation. So kalau saya nak consider the total kinetic energy, so kalau simbol dalam kamu punya nota, dia pakai simbol apa? K ada kiri kanan. So this is what we call average kinetic energy per molecule. Okay, so tadi tu yang kita consider ni hanya translational, hanya yang linear ni. Okay, so here kita nak consider semua kinetic energy. So obviously dia ada dua pergerakan. Satu dia bergerak linear tadi, which is KTR. And then you have to consider the rotational, K rotation. Kita jarang pakai formula ni, tapi ini adalah konsep asalnya lah. So the reason why we consider rotation is because we want to consider total kinetic energy. Dan TR tadi hanya untuk linear. So dia sentiasa 3/2 KT. Kalau jadi kita kena ada tambah rotation. Kita nak tengok sama ada molecules tu rotate atau tak. It depends on the type of molecule. We have 3 types of molecule. We have monoatomic, di. Saya tulis penuh pelik pula satu pilih. Oops. We have monoatomic, diatomic, and we also have polyatomic. Okay, mono for a single molecule. Okay, diatomic ada 2 lah. Kalau poly ada 3. Semua ni satu molekul, sorry. Ada 3 ni dia panggil sebagai polyatomic. Kalau ada 2 dia panggil sebagai diatomic. Contoh monoatomic helium. Okay, diatomic hydrogen. Polyatomic we have H2O. Sometimes dikasih dalam nama, contohnya helium gas. So you have to deduce yourself lah. Helium gas tu dia punya simbol dia He kan, tak ada nombor lain. So dia hanyalah monoatomic. Kalau dia kata hydrogen, then is H2. So H2 adalah diatomic. Okay. So for each of these, KTR dia sentiasa 3. Yang kita dah belajar tadi lah. Maksudnya dia bergerak 3 direction. Okay, rotation ni a little bit different. So for monoatomic, sebab dia single je, contoh dia macam tu. So we assume dia tak boleh rotate. Okay, dia tak ada rotation lah. Kalau dia ada 2 like this, so it can rotate number 1 in that direction. Why? Lagi satu dia boleh rotate macam tu. Saya tak tahu kamu boleh gambarkan ke tak. Saya boleh, tapi saya tak sure kamu boleh tak. So dia boleh gambar rotate Y ataupun X. Dia punya rotation lah. So we put this one as 2 rotation. Okay. And then the last one, polyatomic, actually dia rotate. Katakan ada poly dia ada 3 kan. So it can actually rotate like this. Okay, it can rotate like that. And then it also can rotate like that. Again, nak tunjuk dalam gambar memang tak nampak lah. But worst come to worst, you can memorize this thing. Dia tak susah pun hafal. So this one will be 3 rotation. So if I want to consider the total in terms of half tadi kan, so this one becomes 3, 5, and 6. Okay, this is the numbers that you have to memorize. Okay, this is what we call degree of freedom. We use the symbol F. Okay. And as a result, your K tadi kamu ada a general formula which is F over 2 KT. So if I substitute the values for F2 untuk 3 tu, then it becomes 3 over 2 KT, 5 over 2 KT, and 6 over 2 KT. Okay, so this is the formula. Okay. And then dalam exam, sometimes kalau dia pemurah, they will give you straight away lah. Dia kata, okay, for monoatomic gas, and then you can calculate. So most of the time, they will give you the names of the gas. Contohnya, for helium gas, then you have to consider yourself lah. Saya buat lain. Tapi buat saya rasa dia punya apa tu? Biru tu terang sangat sikit mata. Okay, anyway. You guys understand or not? Ada soalan tak? Yes?
Yes, sir.
Okay, so like I told you before lah, most of the time you might just have to memorize. But remember, this one, especially for poly, it only valid at certain temperature. Okay, temperature roughly around 300 Kelvin. Okay, which is about at the room temperature lah. Let's say room temperature is 30 kan, tambah 273, then you get around there. So all of this is valid at room temperature. As the temperature increase, especially for polyatomic, then the degrees of freedom will increase as well. Okay, so sometimes they might give you a specific degree of freedom. Dia kata for oxygen, for water molecules, dia kata at berapa temperature, the degree of freedom adalah 9 katakan. So kamu pakailah 9 tu, jangan pula kamu insist on using 6. So it depends on the temperature as well. So kalau dia tak cakap, we use the 356. Okay. Okay, so that one is for translational kinetic energy, and then rotational kinetic energy, and then we calculate the average kinetic energy per molecule. The next part is that you want to calculate the internal energy. Okay. Before that, maybe I have to introduce you guys about the principle of equipartition. Sikit je, tak ada apa pun. Equipartition. Okay, it means that the mean average kinetic energy of every degrees of freedom is 1/2 kT. For every degree of freedom, the mean kinetic is half kT. So kalau ada 6 degree of freedom, it becomes 6/2 kT. Things like that lah. Tak ada apa pun. Okay, so the last part. Kalau kamu perasan, saya always tunjuk yang in terms of kT. Kalau kamu tengok nota kamu, dia ada in terms of R juga. Okay, that one is basically you already convert. So tak ada masalah pun, sama je. Cuma kamu kena be careful. Saya tunjuk juga lah. Saya sebenarnya tak suka pakai ni, tapi sebab kamu dah ada dalam nota, so saya takut kamu terpakai secara tak sengaja. Dia ada dua formula. This one yang selalu saya tunjuk. Okay, ini adalah mean kinetic energy per molekul untuk satu molekul. Dari tadi kita cerita pasal molekul kan, so dia adalah untuk satu molekul. Okay, ada lagi satu equation. Okay, yang ni saya tak gambar pakai sebab dia mix things up. Okay, K, tapi kamu boleh pakai, tak masalah. F/2 RT. Okay, ini adalah mean kinetic energy per mole. Okay, satu mole tu tengoklah berapa banyak molekul dia. So this one is for per mole, and yang atas tu adalah untuk per molekul. Nampak macam similar tapi it's totally different. Okay, jangan salah pakai. Okay, hope I make things clear. So biasanya saya suka pakai yang per molekul tu. Kalau nak cari lain lah. Yang second one tu jangan confuse. Okay, and then the last part is about the internal energy. Okay, so by definition, internal energy is basically all the energy for the gas molecules. Okay. So kalau nak ikutkan logik, so internal energy should be consist of potential and kinetic. Okay, but if you guys still remember, ada assumption tu yang dia kata the force between the molecules is negligible. So the potential energy we assume that is negligible as well. So this one is because assumption made. Saya tak tulis dah complete, tapi ini maksudnya lah. So we assume that the force between the molecules does not is negligible. So that's why the potential energy is negligible. So here we don't have the potential energy. Okay, we only consider kinetic. And as you guys know, the kinetic just now we consider for translational and rotational. Okay, so if you already consider both of these, so if you guys still remember, the same. This one is K, right? Okay, this one is for one molecules. So if I want to find the total internal energy for a gas, katakan, so I have to multiply with numbers of molecules. Tak ada susah pun, So N multiplied by F over 2 KT. Kenapa F over 2 KT? Because it depends on type of molecules, whether it's mono, di, or poly. So F2 degree of freedom tu berubah. And then at the same time, okay, sebab nota kamu dah ada, I have to show you as well lah. So K tadi tu can you be written as RT, right? So this one is per mole, so I have to multiply with numbers of moles, N. Okay. And these two represent the internal energy of the gas. So contohnya saya ada, katakan ini kita boleh summary dah ni. Katakan saya ada container. This is my molecule. Katakan this one is hydrogen. Okay. If I want to find the linear punya energy, itu kita panggil apa, guys? Siapa boleh beritahu? Panggil nama ya. Siapa dia? L. L ada?
Ada, sir.
Okay. L, saya nak tanya pendapat kamu. Katakan kita ada molekul semacam ni, kita nak kira dia punya linear energy, kita pakai formula apa? Ataupun kita nak cek kuantiti apa sebenarnya kalau linear tu? Anyone want to help L? Azrina ada? Azrina tak ada. Yang lain? Syazrina?
Yang 3/2 KT tu ke, sir?
Yes, yes. So, kalau kita nak cari linear, kita cari KTR. Okay. So, which is equals to 3/2 KT. Very good. Okay. And that one is for linear punya pergerakan. So, kalau saya nak cari total kinetic energy untuk satu molekul, saya kena consider dia punya rotational as well. Okay. So if I consider rotational as well, then this one becomes K. Simbol dia dah macam ni lah. Okay. This is what we call the mean kinetic energy for a molecule. So the formula will be F/2 KT. So in this case, it will be 5/2 KT lah. Sebab apa? Sebab this one is diatomic. Okay, and then if I want to consider, let's say dalam bekas ni, inside this container, katakan ada 3 molecule. So I have to multiply by 3. So that's why my U becomes numbers of molecule multiplied by F/2 KT. Okay, so this is the punya flow lah. Kalau kamu faham konsep ni, I think it shouldn't be a problem. Kalau kamu tak faham, then it will be a problem because kamu will mix up the formula.